Very good. I suppose technically afternoon now. Good afternoon. Yeah, today I just want to go through the form r cos of x plus alpha and the form r sine of x plus alpha, getting trigonometric expressions into those forms. So the key formulae that we need to know we've already introduced in the compound angle formulae section. So there they are there. So let's start by means of an example. So we'll not do the formal notes like we normally do because it basically is just a process that we're going to learn today. So an example question could be, for example, e.g., write 3 sine theta plus 4 cos theta in the form r sine of theta plus alpha. So that will be an example question. And what I'm going to go through now is how to formally go about doing that. So the way I'm about to do it is more of a proof of how the method works rather than what you do in an exam. I'll go through slightly later exactly how you do it in an exam. But for now, I think it's important just to show you how the process works. Okay, so step one. Take the target form. That's this here. And expand using the compound angle formulae. So I'm going to take r sine of theta plus alpha, and we're going to expand it using this. So you take a moment to do that. So we've got r sine of theta plus alpha equals r times, and here our theta is A and our alpha is B. So r sine theta cos alpha plus, then we've got cos theta sine alpha according to the compound angle formulae, and expand it further. We then have r sine theta cos alpha plus r cos theta sine alpha. So we've got an expanded form of the way we're asked to present the final answer. And that's very, very useful because what we're going to do now is compare coefficients. So step 2, get expressions for r cos alpha and r sine alpha by comparing coefficients. So what I mean by that, so the two terms here are sine theta and cos theta in our original equation, or our original expression rather. So compare the coefficients of our sine theta here and our cos theta here, because if this truly is equal to that, well, equal means that sine theta has the same coefficient as the expression above here, and cos theta has the same coefficient. So actually, the coefficient here of sine theta is r cos alpha. Sine theta has been times by r cos alpha. Likewise, this one's been times by 3. If these truly are equal, then this bit here, that sine theta is multiplied by, has to be equal to 3. So we've got here the coefficient of sine theta, which is r cos alpha, equals 3. we've also got the coefficient of cos theta, which is our sine alpha, equals 4. And that's put us a step closer now to being able to find out what the value of r and alpha are. Right, so the next step, step 3, by doing a suitable division, find the value of tan alpha and hence alpha. So we do this equation here divided by this one. So I call this one equation A and this one equation B. To get tan alpha, it's sine alpha over cos alpha. So if I do equation B, in this case, divided by A, I get r sine alpha divided by r cos alpha equals 4 over 3. R divided by r is 1, the r's cancel, which means that tan alpha is 4/3. So now finding what alpha equals, and I didn't specify whether in radians or degrees. I am going to use degrees for this. So put the calculator in degrees mode, but the question would specify. So I'm going to use degrees for this one. Arctan of 4/3, which is equal to 53.13 degrees. Found alpha. I've got part of the form that I was asked to show it in. I was asked to show it in this form. I've got alpha now. So now I need r. And what I'm about to show you isn't necessarily how you do it in an exam. It's more of a proof of how it works. Again, I said it before, I'll show you how it works in an exam in just a second. So 4 square and add both equations, then rearrange to find r. So equation A was r cos alpha equals 3. So equation A squared is r squared cos squared alpha equals 9. And equation B squared is r squared sine squared alpha equals 16. So I said square and add both equations. So equation A squared plus B squared is r squared cos squared alpha plus r squared sine squared alpha equals 16 plus 9, which is 25. Now if I factorize out the r squared, I get cos squared alpha plus sine squared alpha equals 25. And as you know from first year maths, that's equal to 1. So we're cancelling that out because that bit equals 1. So we've now got r squared equals 25, which means that r equals plus or minus 5. However, in these questions, we typically discard the negative answer because the question would usually just ask for the positive value. So I'm just going to stick with r equals 5. So let's do another. Oh, and I said that this isn't necessarily the way I would do it in an exam. So in an exam, I'd do every other step the same. All of this would be the same, but step 4, basically step 4 is just a cheeky mark. So the ideal exam working so you'd look straight at the question, see the coefficients were 3 and 4. you'd know that you just had to do, well, essentially what is Pythagoras on that. So what you do in an exam, you just write straight away r equals the square root of the sum of the squares of the coefficients, which is 5. So all this is unnecessary, but I just wanted to show you why it worked, because every single time, if you were to do it this way, every time the cos squared alpha plus sine squared alpha would appear equal 1, so we don't need it, and we'd always end up square rooting basically what is the squares of each of the coefficients. So that makes it quite easy. So let's try a different one now. So e.g., write in the form r cos of x plus alpha, an x, r cos of x plus alpha, 5 cos x minus 12 sin x, where alpha is in radians and r is bigger than 0. So have a go at that one. Follow the instructions exactly. So I'll put the instructions back on the screen for a couple of minutes. See how far you get with it. And I think the key step is step 1 about expanding using the trig formulae. So I'll put the relevant formula on there as well. Zoom out a little bit. There we go. So take a few moments. Remember, this one is asked for alpha and radians. So if you've got a bit of a start on that, I'll show you what I would have done. So r cos of x plus alpha is r cos x cos alpha minus or sin x sin alpha. So now the comparing coefficients bit. The coefficient of cos x is r cos alpha. The coefficient of cos x is 5. So we can conclude that r cos alpha equals 5. And this is the key part. The minus sign matches. So we don't need to even consider the minus sign because it's in both of them. So we've got the coefficient of sin x is r sin alpha, and the coefficient of sin x in this case is 12. So r sin alpha is 12. So that implies that tan alpha is the second equation divided by the first to get sin alpha over cos alpha. So 12 over 5, which means that alpha equals, and I specifically said I wanted it in radians, so I need to change my calculator mode to radians here. So arctan of 12 over 5 is 1.176. Arctan of 12 over 5 is 1.176 radians. And now for the cheeky mark that I was talking about, the nice and easy mark. And you can probably do this at the start if you're stuck. 5 squared plus 12 squared, which rather sadly I just remember as 13. They're Pythagorean. It's a Pythagorean triplet. So I've got it. Therefore, our answer is 13 cos of x plus 1.176 radians. And just remembering, I'm just going to check whether I actually concluded with the answer in the previous example. So actually, I didn't conclude with the answer, and I really should have done. I found out what R and alpha are, and usually that's enough to get all the marks, but it's no excuse for answering the question. Therefore, our answer is 5, and in this case, it was sine of x plus 53.13. So always conclude with the answer. So if we were now to do another, let's just say e.g. write sine x, take 7 cos x, in compound angle form, using radians, where r is bigger than 0. So it's our job now to decide which is the best expansion to use. So I'll just put the trig formulae there. There they are there. And we've got to decide which is the best formula to use. So what we want a sine x to appear first, and we want to take sine in the middle, and we want the cos to appear second. Well, the only one that would fit the bill for that would be this here, the sine appearing first, and we have a negative and the cos appearing second. So we can deduce that the one that would give us that would be r sine, in this case x take alpha. So remember, we want the sine x to appear first, we want a minus in the middle, so we'll have to use the take, and we want cos x second. So that's basically what we're going to do. So I'll tell you what, I'll hold back a little bit. So if I hold back a little bit, you try that now, see if you can get the right answer. So I'll hold back just a couple of minutes, let you get on with it. And in every exam question I've ever seen, by the way, you're usually given the expansion that you need to use. You're rarely expected, or I've never seen a case before where you're expected to find your own, but it's fair game for them to ask it. So if you are asked to find which expansion to use as well, this is how you do it. This is how you decide. So expand it, work the magic, then you've got the answer. So expanding that, our sine of x minus alpha equals r sine x cos alpha minus r cos x sine alpha. And then compare coefficients. So you've got sine x there and sine x there, cos x there and cos x there. So that means that the coefficient of sine x, which is r cos alpha, is also equal to 1. The coefficient of cos x, which is our sine alpha, technically minus, but because our question's got a minus in as well, we can just ignore the fact that it's minus. Our sine alpha equals, and that was 7. So doing a division, sine alpha divided by cos alpha gives tan alpha, r's cancel, equals 7. Which means that alpha equals, and I did specify radians, so arc tan of 7, 1.429 radians. And then for the nice easy mark, r equals the square root of 1 squared plus 7 squared. We'll put that in simplified third form. Root of 1 squared plus 7 squared equals 5 root 2. And we've got it. So, therefore, our answer is 5 root 2 sine of x minus 1.429 radians. So that's how you do it. But let's now try and apply it to a few different contexts. So let's take this one, this application, for example. So question from the worksheet that I've put in the live lesson area. So that's it there. So have a go at that one. So express 3 sine x, and it's in degrees. The question's told us it's in degrees. If it didn't put the units next to the x there, then this is a bit of a giveaway because 90 is a key value in trig when working in degrees. So in the context of the question, that's what tells us it's degrees rather than radians. So express it in that form there, and hence describe 2 transformations that would map the graph of y equals sine x onto that graph there. So have a go at that. Take a few moments. So I'll do my solution in just a moment. Right, so maybe try in a different order. What I did before? Get what I called the cheeky mark first. 3 squared plus 3 squared equals root 18, which is 3 root 2. Then expand the given form. So r sine of x minus alpha equals r sine x cos alpha minus r cos x sine alpha, and compare the coefficients. So sine x has a coefficient of 3, then there's a minus sign that matches. Cos x also has a coefficient of 3. So I can see from this that r cos alpha equals 3 and r sine alpha also equals 3, which implies tan alpha is 3 over 3, which is 1. So alpha equals, this is a key trig value, 45 degrees, but let's just put the calculator in degrees mode and check just to be safe. So arctan of 1 is indeed 45 degrees. So now we've got everything we need. So it's 3 root 2. And what we expanded was sine of x minus alpha. So sine of x take 45. And that's part 1 done. Part A rather. Part B, hence describe two transformations that would map the graph of y equals sine x onto the graph. That one there. Well, here we've multiplied by 3 root 2 on the outside of the function. Multiply makes it a stretch by scale factor. And because it's on the outside, it does exactly what it says to the y values. So it times all the y values by 3 root 2. Parallel to the y-axis. Any outside transformations done to y. And then the second one, inside. So it does the opposite of what it says to x. Translate. So it's telling us to take 45 from the x's, but we know better. We know that because it's inside the bracket, we're going to do the opposite. So we're going to translate it by positive 45 and none in the y direction. So that's that one there. So another application that you could possibly see for this one would be something like this. So I'll put a question on there. So there's another. Express each of the following in the given form, where r is bigger than 0 and alpha is between 0.5 pi. Now it hasn't told us specifically radians, but from the context we can see it's radians because it mentions pi over 2. If we're talking in degrees, then that pi over 2 would never come up as an angle. So contextually, we know we're in radians now. So let's put our calculator straight in radians. Right. I'll just get rid of the second question. We're only going to do one of these. So express it in the given form. Express it in r sine of x minus alpha. Give the exact value of r and alpha corrected 2 decimal places where appropriate. And I'm going to make my own part B to this. So a different context that we could put on this would be part B. Find the maximum value the function can take and the smallest positive value of x for which this maximum occurs. So do the first bit yourself. By now you know how to write that in the given form. And the new part, part B, is what I'll go through with you in a second. So I'm just going to quietly get on with the first part myself. You do it concurrently and just check your answer against mine. So that's for 2 decimal places where appropriate. So 0.59 radians is the value of alpha. So therefore our answer is, and r was root 13 sine of x minus 0.59 radians. So find the maximum value of the function. Find the maximum value the function can take and the smallest positive value of x for which this maximum occurs. So the maximum value the function can take, well, the sine function normally takes maximum value 1. But we know better than that. We know that it's been stretched by scale factor root 13. So the value is no longer 1. The maximum value the function takes is now root 13 because it's been stretched parallel to the y-axis scale factor root 13. So max equals root 13. And the smallest positive value of x for which this occurs, well, the maximum of sine we know occurs at 90 degrees. Or in this case, we're in radians, pi over 2 radians. So the angle we know is pi over 2 radians. So the angle, doing the same colour, the angle x minus 0.59, we know has to be pi over 2 radians, because what's in this bracket has to be pi over 2 for it to be a maximum. The maximum of the sine graph occurs at pi over 2. So just rearranging that now, x equals pi over 2 plus 0.59 equals, we'll just put that in the calculator, pi over 2 plus 0.59 equals 2.16 radians. So that's how we do that one. So we'll do one more example where we have to solve an equation. Then we'll move on, and I want to do a little bit of small angle approximations in this lesson as well. So basically, this is a useful format to have things into solve equations, because most of the equations, when you did your first year maths and your first year trigonometry, most equations were written already in this form for you to easily solve. So that's another use of this. If you're given an equation like this and it just says solve it, and this question's been a little bit kinder than just having us say solve it. This question's actually asked us in part A to put it in a solvable form, then asked us to solve it, so it's a bit kinder, but you could be expected to make that deduction yourself. So have a go at that, right, in the given form. Then solve. I'll go through it in just a moment. So I'll just quietly get on with this while you're all working as well. So this is a key trig value that I should know, but admittedly need the safety net of a calculator, pi over 6. Therefore, our answer is 2. Cos of x plus pi over 6. And 2 is bigger than 0, fulfills the requirements. And pi over 6 is between 0 and pi over 2, again fulfills the requirements. So part B, they're asking us to solve the equation. So once the answers from 0 to 2 pi, however, we're solving it not for x currently, we're solving it for x plus pi over 6. So at each side, pi over 6 is being added. So we're solving for all the multiple solutions between pi over 6, because we'll add pi over 6 to each limit, and 2 pi plus pi over 6. Shocking that I'm resorting to a calculator to work out what should be simple fractions, but in an exam situation, you might be nervous. You might be feeling the pressure. Even do the simplest of calculations on the calculator so you don't make a mistake. Accuracy is so important. So 13 pi over 6. And that's the range in which we're searching for our multiple answers. So it's asking us to solve that equation that we've just reduced. It's asked us to solve that being equal to 1. So we know better now. We know that we've done a bit of work that will allow us to write in a nicer and more solvable form. So notice it's the same expression on the left-hand side as we let's call it trig factorized earlier, wrote in the compound angle format, and it's equal to 1. So that's what we're solving. So the first thing I'm going to do is divide by 2. So I've got cos of x plus pi over 6 equals 1/2, and we're ready to solve. If we arc cos both sides, we get x plus pi over 6 equals, and let's arc cos 1/2, which is 1/3 pi. So whatever you do, as I told you in the trig lesson, don't take pi over 6 yet. We want to find the multiple solutions that match with pi over 3. So rough diagram, cos graph, not between 0 and 2 pi, between pi over 6 and 13 pi over 6. So what I'm going to do another part cycle just to be safe. So we got 0, pi over 2, pi, 3 pi over 2, 2 pi, and overshooting it a little bit, but just to be safe, 5 pi over 2. So there's potentially 3 solutions, and after we've found each of these 3, we're going to check whether it's in this range here and discard the ones that aren't. So we've got our first pi over 3, which, starting at the top of the hill, is pi over 3 from the top of the hill. Likewise, we've got another solution, another 2 solutions, each pi over 3 from the top of the hill. So we've got 2 pi minus pi over 3. Which is 5 pi over 3. And we've got 2 pi plus pi over 3. Which is 7 pi over 3. Now it's debatable whether this is an answer to include. Is this inside or outside the range, 13 pi over 6? Well, let's check. So 7 pi over 3 is about 7.33. 13 pi over 6 is 6.80, or 6.81 if I round properly. So indeed this is outside the range, so we can discard it at this early stage. And now all that it takes is for us to take pi over 6 from each of those. So x equals pi over 3 take pi over 6, which is pi over 6, and 5 pi over 3, that's 10 pi over 6, take pi over 6, which gives us 9 pi over 6. Again, in an exam situation, do the simplest of calculations on your calculator, because if you simplify wrongly, you lose a mark, and that could be the difference between an A and a B, A star and an A, B and a C. It could, if you're on the grade boundary, it's really not worth doing calculations in your head. So I'm going to practice what I preach and do this, what should be a simple calculation on the calculator. 3 over 2 pi. And there are our two answers. So that's basically the styles of question that they can ask you on compound angle formulae. And normally this is where I'd end, but I wanted to get in a little bit about small angle approximations as well. So in the time we've got left, do a little bit of small angle approximations. We're not going to do any notes. I'm just going to give you an example of how to do some of the questions, because they do catch some people out. So let's first of all, I'll put on the screen the small angle approximations, which you are given in your formula sheet in the exam. So whichever exam board you're on, you are given them either a sheet at the front of the paper or a separate formula booklet, depending on your exam board. So there's our small angle approximations here. And when angles are small, and small isn't really defined, but we're talking possibly about 0.1 radians if I were to put a number to it, but that's not official, that's just my judgment. But for the small angle approximations to work, sine theta approximately equals theta, cos theta approximately equals 1 minus a half theta squared, and tan theta for small angles is approximately equal to theta. So I just want to go through a few examples of the sorts of questions that they could ask you. So, example question here. When theta is small, show that the expression 4 cos of 3 theta minus 2 plus 5 sine theta over 1 minus sine 2 theta can be written as that there. So we're going to apply each of these formulae here. So theta is small, so cos of 3 theta, so we've replaced theta with 3 theta here, so we'll replace theta here with 3 theta, and don't forget it's all of the 3 theta that has to be squared, all of it. So we've got 4, then cos of 3 theta becomes 1 minus a half of all of 3 theta squared, and this is where most students go wrong. They forget to square all of the angle. So key points, square all of the angle. 1 minus a half theta squared, in this case 3 theta squared, take 2, plus, and sine theta just approaches theta. All divided by 1 minus, and sine of 2 theta approaches just 2 theta. So then have a go at simplifying that. So equals, multiplying out the bracket, 4 minus, so a half of 3 theta squared, 4 lots of a half of 9 theta squared. So running out of room, so I'll put it on the next line. So 4 minus 4 lots of a half of 9 theta squared, take 2, plus 5 theta, all divided by 1 minus 2 theta. And keep on multiplying that out and simplifying. 4 minus, so 4 over 2 is 2, so that becomes 18 theta squared. Take 2, plus 5 theta, over 1 minus 2 theta. So keep going with that. Equals. So 4 take 2 is 2. Plus 5 theta. Take 18 theta squared. All divided by 1 minus 2 theta. And you'd be forgiven for thinking that it's you've come a little bit unstuck now, because there didn't seem to be anything else to do. So my gut reaction now is to try and quadratically factorize the numerator. So rather than messing around and trying to search for factors, we can just use the solver to make it quicker for us. So polynomial degree 2, so minus 18 theta squared plus 5 theta plus 2, and hopefully it'll give us rational answers. So yeah, a half. So just a little bit of a sideshow here. Theta equals 1/2 and theta equals minus 2/9. I can reverse engineer factors from that, multiply by 2. So I'm going to make these answers so that there's no fractions and make the right hand side 0. So double it. 2 theta equals 1. So 2 theta minus 1 is a factor. So I'm basically reversing the factor theorem here. 9 theta equals minus 2. So 9 theta plus 2 is a factor. So there I've got my factors from reverse engineering the factor theorem. So equals 2 theta minus 1. 9 theta plus 2. However, notice that this doesn't give me negative 18 theta squared. So I'm going to have to do something to make one of the answers negative. Well, that's nice and easy. I could just make the first factor negative, so change it to 1 minus 2 theta to give me the one I need. 1 minus 2 theta, like that. There we go. Over 1 minus 2 theta. That divided by itself equals 1, to give 9 theta plus 2 as required. So then write down the value of that when theta is small. So small means close to 0. So what we can do here, part B, as theta becomes small, i.e. as theta approaches 0, the function 9 theta plus 2 approaches 2 because theta is becoming 0. Therefore, function has value 2. So basically, that's it. Really, that's small angles for you. That's everything pretty much covered. So they're all the pitfalls that you could fall into, or the traps you could fall into. So I think that's really it for today. Go away and practice some of the trig questions from the worksheet I've just put up, and also go away and practice some small angle exam questions from my website, all of which have the answers on. So yeah, bit of a shorter one today. We shall leave it there. Have a good one, and see you next week. You're welcome.